Hi everyone, my name is Tracy Doan. This is Jenna Williams, and we are a graduate student at Cal Poly San Luis Obispo, majoring in architectural engineering. And today we wanted to discuss with you our research on the assessment of modeling strategies for lightly reinforced concrete structural walls. This is our outline for today. We'll start off with research motivation and conclude with the future research and some final remarks.
Before we dive into the project, we wanted to give you some structural engineering terminology that we'll be using throughout the presentation. First, we have gravity loads, which refer to the load of everything inside the building that'll be weighing down on the structural elements, such as the walls. Second, we have lateral loads, which refer to the load of wind, or in our case, earthquakes, on the walls that cause a building to drift from its neutral position. And lastly, we have reinforcement ratio, which refers to the ratio of concrete to rebar that you would find in the cross-section cut of a wall. The reason we care about lightly reinforced concrete structural walls is because they've behaved poorly in past earthquakes such as those that happened in New Zealand in 2010 and 2011. For these brittle, non-ductile walls, it isn't so much strength as it is drift capacity that is an issue. Many of the walls that performed poorly were characterized by three main components: low gravity loads, light steel reinforcement ratio, and no boundary elements, which means that there was no concentrated steel at the ends of the walls. Not only does damage like this lead to loss of structure, but it also means that we lose homes, workspaces, and everything that goes along with providing a community. Poorly performing buildings isn't just a problem for engineers, it's a problem for our society to choose to solve. A study by the Concrete Coalition indicates that there are 16,000 to 17,000 pre-1980s buildings in California that are vulnerable to this type of damage. And given the high seismic nature of where we live, the chance of facing a disaster similar to New Zealand only grows. The dense blue dots on this map of LA indicate a high concentration of buildings that fall under a non-ductile concrete ordinance, which requires building owners to retrofit them. Industry practitioners want to understand how to fix these buildings, or how to fix these walls, and that's where we, as student researchers, hope to assist the industry.
One of the recurring issues in the industry is not being able to predict the failure mode of these walls. So the first task that we took to this project was to assist two graduate students from last year test their baseline wall. And this baseline wall is a replica of a vintage vault wall. It was subjected to lateral loading to a specific target displacement. So the result was being recorded on a plot called a hysteresis plot on the right. This is plotting percent drift in the x-axis, which is how much the wall had moved from its original position. And on the y-axis is plotting load, so how much load the wall is able to resist throughout the loading cycle. The overall result of this test indicated that the wall failed through significant base rotation. It also had very minimal concrete crushing and rebar buckling. This is important to us because it shows that the wall failed through tension control failure, whereas the industry had previously predicted that the wall would fail through compression-related damages. Because of the contradiction to the industry's prediction, we decided to look at other specimens. So on the left was the wall from Cal Poly that I discussed earlier. On the right is the wall from the University of Auckland, New Zealand by Liu et al. The common ground in these two walls is that they both exhibit pre-1980s characteristic, and they're also, after testing, they were found to have flexural tension failure as well as rebar fracturing.
So if we know that these walls aren't being predicted correctly in industry, our main goal with our research is to accurately predict the failure modes of these walls. And we pursued three different methods of predicting this. The first two are simplified pushover analyses, and we used a textbook method known as Priestley and a code-based method known as ASCE 4117. We also looked at a software analysis using Perform 3D under a cyclic load analysis. The first prediction method we pursued is called the Priestley simplified pushover analysis. A cross-section cut of the wall is analyzed under an increasing moment load to characterize the behavior of the wall. The curvature or rotation of the wall can be plotted against the moment capacity. From the moment curvature analysis, we were able to relate the rotation of the wall to the drift or displacement of the wall and find the corresponding force that would lead to the failure. The force displacement plot on the right is commonly referred to as a pushover plot and is used by engineers to evaluate the behavior of a wall. The second prediction analysis we pursued is the ASCE 4117 method, which is most commonly used by industry practitioners in the United States. For this method, the wall is expected to rotate at a calculated height above the wall by a rotation given in the code's tables. From this rotation criteria, the wall pushover curve can be plotted in a similar way that we previously saw for the Priestley method.
The third analysis method we pursue is on a analysis program called Perform 3D. This is a sophisticated nonlinear analysis program that allowed us to model the wall as a cantilever. We're able to distribute earthquake loading and gravity loading throughout the top of the wall. We're also able to break the wall up into smaller cross sections that allowed us to embed steel fiber and concrete fiber to capture the geometry more accurately. We loaded the wall the same way that the experimental testing had loaded it, and we plotted again on the hysteresis, but we're only interested in the envelope of the hysteresis highlighted in the red because this would give us initial stiffness, the wall strength, and the amount of energy dissipation throughout the loading cycle. We wanted to use this Perform 3D model to calibrate to the experimental test result and get an accurate prediction. So with that, we decided to explore two parameters on Perform 3D, the effective meshing and the effective stiffness factor. Meshing allowed us to break the wall up into smaller pieces to observe what's happening at each node. We decided to go with 3 different meshing configurations, and we plotted them on the hysteresis against the experimental result to see how closely they match. And what we found from our wall is that the taller the wall is, the more meshing that is required in order to capture the peak drift and the peak capacity of the wall. The other factor is the stiffness factor. This is a ratio of the amount of energy being dissipated throughout the loading cycle. This focuses on the envelope of the hysteresis. So we decided to explore a stiffness factor of -1, 0, and +1. And what we found after plotting the envelope against the experimental envelope is that for our wall, the stiffness factor of 0 best matched the experimental results.
After exploring the different prediction methods, we were able to determine each method's accuracy as it relates to the experimental pushover results shown in the black dotted line. The Perform 3D model was best at capturing the stiffness or the initial slope in the plot. All of the methods were acceptably accurate at capturing the peak strength of the wall, but neither the Priestley nor the ASCE 4117 methods were able to accurately capture the drift capacity of the wall. Because Perform 3D does have the capability to find drift, cyclic degradation, and energy dissipation, it was important that we refine our Perform 3D modeling. Our current Perform 3D models are drift controlled, so our next modeling step requires us to implement a pushover test in Perform 3D with strain gauges on the concrete and steel to determine failure. Our second modeling objective is to explore adding different nonlinear material models to our analysis, including a concrete tension model that could properly capture the unique failure of the wall we are investigating. Our third objective is to study the capabilities of other software that industry practitioners commonly use, such as eTabs and SAP 2000.
In order to prepare us for the next step, we sent out an industry survey to ask engineers in practice questions about their walls' material properties, the wall geometry, how they analyze their walls, and more importantly, the retrofit process that was being pursued. And we're hoping that with the data gathered from this industry, the next team can come in to design the wall, build, test, and retrofit it. Before we conclude our presentation, we wanted to highlight to you the importance of the retrofit process and the overall goal of our project. Everything starts with the city ordinance trigger a seismic evaluation, and then 3 important questions come into play. And that's whether the building owner will pay for the upgrade. If they will, then the engineer will evaluate the building, and then the retrofit is designed and sent to a plan checker, and then retrofit will be implemented. But a lot of times this doesn't happen, so the building gets demolished. When the building gets demolished, this creates a huge dent in our economy and the sustainability of the building system. So we take on this project as our main goal in order to accurately predict the failure mode of these walls, to assess the reliability of the retrofit solutions, and also give feedback to the industry. And we're hoping with this, we're able to reduce the number of carbon footprint, as well as reduce the number of failed abandoned concrete buildings that were deemed irrecoverable.
A project like this isn't possible without a village, and so we'd like to thank our industry advisors, industry support, Cal Poly CAD Student Support Shop, and the funding we've received from within Cal Poly and outside of Cal Poly. We couldn't have done it without them, and we look forward to their continued support in the coming years that this project continues. Thank you for your attention, and we look forward to answering your questions.